we're going to talk about the third kinds of proofs. So we have talked about direct proof, if P then Q, which means we assume the P statement, we prove Q statement. Or we can prove by control positive. That means if P then Q, we prove if not Q, we assume not Q, then we prove not P. That's control positive. Then today we're going to talk about proof by contradiction. What does that mean? Remember, we have a statement like conditional statement, something like for all x in the integers, right? Something like that for all. Contradiction is there is, if something for all is true, the statement, to say for all something, if we want to disprove, disprove is a kind of proof is not true. If we want to prove the statement is not true, it's a false statement, we can prove by contradiction, which means we find one counterexample to say, okay, you were saying for all this is true, but as long as I find one thing which is not true, that proves the whole statement is false. So that's called a proof by contradiction. So let's go through these slides. Proving statements with contradiction. In this chapter, we will prove that a statement R is true by the method of contradiction. So that is, we will assume that the entire statement we're trying to show is false. So the statement, we try to show the statement is a false statement. That is not R, right? So negation of R, not R, is true. And reason until we find another statement C such that not R implies C and not C. Since it's impossible for both C and not C to be true, because we know what's, C and not C, right? C and not C has no intersection. This means that our original assumption of not R must be false, so implying R is true. So when we begin the proof, we do not know what the statement C will be. This is just an abstract idea. Let's see, what does this mean? So a classic example of a proof by contradiction goes back to Euclid. We know Euclid, right? We're using Euclidean space. So it's not a conditional statement. So let's see this one, proposition. There are infinitely many prime numbers. Okay, there are infinitely many prime numbers. So numbers, we either call prime numbers. So this is in a set of counting numbers or natural numbers. Natural numbers, remember, are counting numbers, 1, 2, 3, 4, so on and so forth, right? When we factor number, we want to put the number in a prime factorization. So prime numbers are 2, 3, 5, 7. It has two factors, 1 and itself. If a natural number is not prime number, it will be we call composite number, which means it can be factored with two factors. Let's see, 6. 6 can be factored as 2 and 3, or 1 and 6. So there are two ways to factor the number. Let's prove this by contradiction. So we assume the statement is false. So we assume the statement is false. So we'll see, okay. There are finite many prime numbers. So that means, which means the numbers can be counted, Excuse me. Excuse me, let me get some water. Sorry. So we'll assume this statement. We assume this statement is false, which means that finite many prime numbers. So which means we can list the numbers like P1, P2, P3, right, up to Pn. While P1 is the smallest prime number, 2, P2 is 3, P3 5, so on and so forth. Okay, Pn is the nth prime number, is the largest prime number because there are only finite many prime numbers. That means we can count. We can put those numbers into P1, P2, P3, up to Pn. So let's consider the number A. So A, we just pick any number. So this number is P1 multiplied by all those prime numbers multiplying together. So the product of all those prime numbers, then we add 1 to it. So we add 1 to it. And what kind of number is A? Right? So this number A will not be divisible by P1, will not be divisible by P2, will not be divisible by P3 up to Pn because we add 1 to it. So that basically gives us this A is another prime number. Basically, it's a contradiction, right? So the number that's the product of all prime numbers plus 1. Like all natural numbers, A has at least 1 prime divisor. Right? This means for some natural numbers K, K is in between 1 and N, we have a PK divides A. Okay, so this is another kind of argument. Well, we could just say, right, well, this K we can use I, most of the time we use I. So either, P1 divides A, P2 divides A, any PI divides A, and this I is in between of 1 and N. So here, we use K. So which means we must have a prime number, PK divides A. So this PK could be P1, could be P2, could be, up to Pn, any of these prime numbers. But by definition of divisors, there must be an integer C such that A equals to C multiplied by PK, right? So, because A is a natural number, and if A is not a prime, that means A has a factor of a prime and something else too, at least 1 prime. So that means A can be written as A equals to C times a prime number. C is just some integer. It can be prime or doesn't have to be a prime, just some integer. So this means, so A will have 2 ways of writing it. So one way is A can be written as this, the product of all prime numbers plus 1 and a prime factor times C. So we have this equation. So all the product of primes plus 1 equals to some C multiplied by PK. PK is one of these prime. That means we can divide both sides by PK, right? We can divide both sides by PK. So what do we get? If we do that, with this equation, we divide the PK on both sides. We get C equals to all the product of prime numbers except the PK form, PK prime, right? Because we divided by PK. And the 1 has to be divided by PK. 1 divided by PK. Well, PK, remember, PK is the least. So the smallest PK could be is 2, right? PK could be 2, could be 3, could be 5, could be 7, so on and so forth. It could be one of these prime numbers. Well, let's keep going. Let's subtract the product from both sides. So we get 1 divided by pk equals to 1 integer, subtract another integer, because the product of some prime numbers is an integer, right? And the c also is an integer. But 1 over pk won't be an integer, because the smallest prime is 2. So this number is it could be half, could be 1/3, could be 1/5, could be 1/7, so on and so forth. So step A is saying the left-hand side of the above equation is not an integer. 1 over pk is not an integer, right? So hence the right-hand side of the above equation, but the right-hand side is an integer. So this is a contradiction. So we find one contradiction. So meaning the original assumption must have been false. So because this contradiction is derived from this assumption, right? We assume something. So that means this assumption has to be false, has to be false assumption, which in turn proves there are infinite many. They cannot be finite many prime numbers, because if there are finite many prime numbers, we arrive a contradiction. The contradiction is we will be able to write a fraction as an integer. That's a contradiction. Okay, so this is, I think this is a lot. Anybody has any questions? So the proof goes by contradiction, right? So the proposition is there are infinite many prime numbers. It's difficult to prove something infinite, right? It's difficult to prove case by case. So how do we prove it? We make an assumption, we make a false assumption, we arrive at a contradiction. Is this an average question? Yeah, some questions in some proofs in mathematics, some theorems in mathematics, can be proved by contradiction. So this one is saying that infinite many prime numbers, right? To prove by direct proof is very difficult. It's almost impossible by direct proof. So it's much easier to prove by contradiction. So how do we prove by contradiction? We assume the statement is false, right? So think about the statement is false as P, right? So there are finite many prime numbers, right? If P, so this is if P. If we can arrive Q, well, that's fine. But we arrived at a contradiction, at something, contradicts to our common sense, or contradicts to the definition of an integer and a fraction. So, the contradiction is the definition of integer equals the definition of an integer. So that's a contradiction. So because we assume the assumption is false, so we derived a contradiction. So the contradiction is saying the assumption must be false. So the assumption is there are finite many prime numbers. So it's a false means not. They're not a finite many prime numbers, which means there are infinite many prime numbers. So the steps are, assume that only finite many prime numbers. So write those primes, P1, P2 up to Pn, because they're finite many. So we name them. Then we say, okay, let's just use the product of those the finite many prime numbers. Then we add 1 to it. So we made another number. Of course, right? There are infinite many natural numbers. So we can always multiply the prime numbers, then add 1 to it. So one way is this. Then another one is saying it's in fact any natural numbers, so A is a natural number, right? It has to have divisors as prime numbers. So we just assume, pk divides A. So A as a factor of prime. So this prime is any prime, in P1, P2, any of this, from P1 up to Pn, just pk represents any one of this. So assume pk divides A. Then A can be written as C times pk. So A can be written in two ways. So A can be written as a product of all those prime numbers plus 1, and also C times pk. So we equalize those two. We equal those two. Then we divide by pk on both sides. So we get the product of primes except pk. Then plus 1 divided by pk equals to C. Right? Basically, the equation was divided by pk on both sides. Then we subtract this one, subtract the product of those prime numbers from both sides. So we get 1 over pk, so we get a contradiction. Get a contradiction here, right? We get a contradiction. Where is the contradiction? On the left-hand side, 1 divided by pk. Think about pk, could be 2, could be 3, could be 5, could be 7, so on and so forth. So 1 over pk is not fraction. But C, the right-hand side, C minus the product of those prime numbers, still integers, because we have a counting number, subtract another counting number, right? It has to be an integer, cannot be a fraction. So this is a contradiction. Since we arrived at a contradiction, we go back to say, okay, the assumption must be false. So this is how to prove by contradiction in general. All right, let's keep going. So one common type statement for which a proof by contradiction works well are those of the type for all. All right, for all, a statement for all. For all, so the statement has a condition for all. When we use contradiction, we just need to find that there is one. Remember negation? We want to negate for all. What's the negation for all? There is one. There is one to make a P not true. So not for all follow the statement. That means equals to there is, one thing makes the statement not true. So this is proved by contradiction. For example, if you want to show by contradiction the statement, every student in the class has a cat, so you only need to find that there is one student in the class who does not have a cat, right? Everybody in the class has a cat. Well, maybe Bob doesn't even have a cat. So that proves the statement is false. I find one example, one counterexample. Okay, let's see this proposition. For every positive real number x, right? So x is a positive real number. X divided by x plus 1 less than x plus 1 divided by x plus 2. Oh, this is an inequality, right? So this is for every real number. So if we want to prove this is false, all we have to do is find one example, one counterexample to negate this. All right. note, we cannot only use one number to prove, all right? It's not correct to see that, okay, if x equals 2, then 2 over 3 less than 3 over 4, right? This is just one example, right? Hence, the proposition is true. No, we cannot do that. The proposition states that statement x divided by x plus 1 less than x plus 1 divided by x plus 2 is true for all positive real numbers x. So showing only for one number, which is not true. So we have to prove by contradiction. We assume it's false. All right, we assume this is a false statement. No, we assume this is a false statement. So we will assume the proposition is false. Suppose there exists a positive real number x such that this is not true. Right? We suppose the statement is false. This means there exists a positive real number such that the inequality is opposite. It's x divided by x plus 1 greater than or equal to x plus 1 divided by x plus 2. Well, what's less than or equal? What's the opposite of less than? It's a greater than or equal to, right? Okay. Since x is positive, x plus 1 and x plus 2 are all positive. So their product is positive. So we can then multiply both sides by x plus 1 times x plus 2. Yeah, we flip the sign. Yeah, basically that's a negation, right? If one, let's say 1 less than 2. What's the negation of 1 less than 2? It's 1 greater than or equal to 2, right? Okay. So we want to get rid of the denominators. So we multiply x plus 1, x plus 2 on both sides. When we do that, we have this. So we simplify. We have x plus, so the inequality becomes this. X times x plus 2 is greater than or equal to x plus 1 times x plus 1. Or let's simplify those both sides. So one side we simplify, we have x squared plus 2x. The other side we simplify, we have x squared plus 2x plus 1. Where x squared is positive, 2x is positive. We just subtract those two. So we get 0 greater than or equal to 1. Contradiction. Right? Obvious contradiction. So since this is a contradiction, so since we arrived at a statement not true, 0 greater than or equal to 1, we know it's not true. So if it's not true, then we go back. We say, okay, the assumption must be false. So this is assumption. Suppose. So this assumption must be false. In turn, this proves this is true. Okay, you see the step? The proposition, we want to prove this a proposition. Right? How do we prove this proposition? It's difficult to prove for every positive real number x, you know. It's difficult. Of course, later on, we're going to talk about something called induction. You know, sometimes we can prove by induction. But for such case, we can prove by contradiction. So how to prove by contradiction? We assume the statement, the proposition is false, right? Then we arrive at something contradiction, or arrive at a contradiction. Then because we arrived at a contradiction, we go back to say, okay, the assumption must be false. Since our assumption, which negates the proposition, is false, so that in turn it proves the proposition is true. Okay, anybody has any questions? All right. Okay, proving conditional statements by contradiction. So we want to show. So yeah, we negate the whole proposition. You are right. You see, in both cases, we negate the whole proposition. So this proposition is saying for every positive real number x, and this is true, less than, so the less than sign, right? And we want to negate this. We want to say, okay, not assume not the proposition, which means how do we negate the whole statement? Every becomes there is, right? And less than becomes greater than or equal to. Right? We negate. So assume the proposition is false. So which means exist one number such that this, the left-hand side is greater than or equal to the right-hand side. We negate the whole proposition. Yeah, please ask if something is confusing. Okay, let's see. We have a conditional statement. P implies Q. We want to show, let's see how to prove by contradiction. P implies Q by contradiction. So we will need to assume that entire conditional statement is false. So we want to negate the whole thing. We want to negate the whole thing. We assume this. We assume not P implies Q. Okay, not P implies Q. Since P implies Q is logically equivalent to, remember that, not P or Q. Remember, we use truth table. Not P or Q. So we have this equivalent statement. Not P implies Q. Not P or Q. Right? P implies Q. As long as Q is true, the statement is true. So only not P. So not P or Q. So negation of not P or Q. So not P, which means is P, right? Not or means and. Not or, not, this not, and this or means and. Of course, not Q is not Q. Okay. So this is very similar to De Morgan's law. All right. We talk about the sets and the sign. So this goes along with De Morgan's law. So we want to prove not this conditional statement. It's the same to prove P or a P and not Q. P and not Q. So if we assume P implies Q is false, we need to assume that P and not Q is true. So we want to assume this is true. Then the reason until we reach a contradiction. Well, let's see this proposition. Suppose A is an integer. If A squared is even, then A is even. Right? Suppose A is even, then suppose A squared is even, then A is even. Of course, we can prove this by direct proof, right? We can prove this by direct proof. Just read out, if A squared is even, you'll go from the definition of it. But let's try to do this to prove by contradiction. Excuse me. So statement A squared is even, let's treat as P, right? A is even is Q. So this statement is if P then Q statement. So what do we want to do? We want to assume P and not Q is true, right? Then we arrive at something contradicts to a truth. So P or not Q is true. So we assume this. So P is A squared is even, right? That's P. Not Q means not A is even. Well, if it's not even, that means A is odd, right? A is odd. Or let's assume that. So we assume A squared is even and A is not even. So if A is not even, that means A is odd. So A squared is even and A is odd. If A is odd, remember we can write A as 2B plus 1 or 2C plus 1, for C be some integer. And A squared is even, remember A squared, so let's write out A squared. A squared equals 2C plus 1 squared equals 4C squared plus 4C plus 1 equals 2, we factor out, 2 times 2C squared plus 2C plus 1, right? What kind of form is this? So the A squared can be written as 2K plus 1, where K is the expression inside the parentheses with 2C squared plus 2C. This fits the definition of odd integer. So if A is odd, A squared is odd. A squared is odd, right? So we showed A squared is odd, but we assumed A squared is even. So that's a contradiction. That's a contradiction. So therefore, the original assumption, so this assumption has to be false. Has to be false, right? Has to be false. Okay, any questions for this one? Oh, that's how we, let's go back a little bit. We did negate the whole statement. Let's go back a little bit. You see, when we negate the conditional statement, we have this equality. This we need to remember. When we negate the whole statement, the whole conditional statement, that's equivalent to P and not Q. Okay. Yes, Moises. The not outside has to be distributed to any part of the statements. That's right, you're right. Because we're negating the whole thing. We're negating everything. Okay, so prove this. We assume A squared is even and A is not even, right? Just this, remember this. This is the equivalent statement as not negate the whole statement. Oh, I see. Okay, let's see another proposition. If A, B are integers and A is at least 2, right? Integers, so A is at least 2. So that means A can be 2, can be 3, can be 4, so on and so forth. Then A does not divide B, or A does not divide B plus 1. Okay, so this is saying A, B being integers, and 2 is an integer at least 2. Then either A does not divide B, or A does not divide B plus 1. So let's prove this by contradiction. So we want to negate, right? Okay, let's figure out the P and Q. So a P is this, right? If P is A, B integers, and A greater than or equal to 2. Q is this. Q is a composite statement also. Q is A either divides B or A does not divide B, or well, let's say this one. Either A is not a factor of B or A is not a factor of B plus 1. Okay, whenever you see A does not divide B plus 1, that means A is not a factor of B plus 1. So prove by contradiction. Prove by contradiction is P and not Q, right? We'll assume P and not Q, not Q. So suppose there exists AB with this, right? So suppose P part, P still P. Now not Q. Let's see what's not Q now. It's not true, so we negate both. It does not divide B or it does not divide by B plus 1. So it's not true that A does not divide B or it does not divide B plus 1. By De Morgan's law, it does not divide B or it does not divide B plus 1 is not true. So negation of these composite statements means either that means A divides B and A divides B plus 1. So we're negating A does not divide, right? So negation of A does not divide B means A divides B. Negation of or becomes and. Negation of A does not divide B plus 1 becomes A does divide B plus 1. So negation of Q becomes this. So not Q is A divides B and A divides B plus 1. So by definition, if A divides B, that means B can be written as A times another integer, right? C, let's call it C. C is an integer. And A divides B plus 1 means B plus 1 can be written as A divided by another integer. Let's call it D. So B plus 1 equals A times D. D is another integer. Well, let's subtract those two. Let's subtract AC from AD, right? So subtract AD from AC. That means we're subtracting B from B plus 1. So B plus 1 minus B equals 1. So we have AD minus AC equals to 1. We'll factor out A. We have AD minus AC equals to 1. Factor out A. That's A times D minus C equals to 1. Right? Remember that. Remember A is an integer. D, C are integers. Right? So since A is positive and 1 is positive, and this implies D minus C is also positive. It's positive integer. Right? So let's divide D minus C on both sides. So when we divide D minus C on both sides, we get this. We get A equals to 1 divided by D minus C less than 2. Which is this number, 1 divided by D minus C. Remember, we assumed A is greater than, or here we assumed A greater than, A is at least 2. We assume A is at least 2, right? So we get this. So we get A equals to 1 divided by D minus C. Y is less than 2. Oh, okay. Because D minus C is a positive integer. this implies that d minus c is a positive integer because of this. Because a is an integer, 1 is an integer positive, 1 is positive, a is positive, and a is at least 2. A is at least 2, right? So we have 1 divided by d minus c. Because d minus c has to be positive. D minus c has to be positive. Well, how many positive integers? Well, positive integers 1, 2, 3, 4, right? Those counting numbers. And we don't want a to be 1, right? Because a we assumed is greater than or equal to 2, at least 2. So a is at least 2. A is at least 2. But 1 divided by this number, because this number is at least 1, right? D minus c, because it's a positive integer, is at least 1. It's at least 1. If it's 1, it's just 1. So one way we see this is 1 over a positive integer is less than 2, but we assumed our assumption is saying a is at least 2. So those two contradicts to each other. So we arrived at a contradiction. So this contradicts to our assumption. Because we have this contradiction, we said our assumption must be false. So this is a proof by contradiction for conditional statement. We assume something false, then we arrived at a contradiction. So the contradiction is saying the assumption has to be false. Okay, any questions? All right. You know, some obvious contradiction in mathematics are those. You know, sometimes when we solve, remember when we solve system of equations, right? System of equations, if we have two system of equations, there's no solution. Usually we end up with something like 0 equals to 1, right? 0 equals to 1, which is a false statement. Or 0 greater than 1, sometimes we encounter in other situations. Or a is odd and a is even, impossible, right? A either odd or even. Or a is greater than 0, or a is at least 0, contradiction. Or a is an integer, or a is not an integer, right? Contradiction. Okay, that's it. Anybody has any questions?
Yeah, Professor.
Yeah.
For the final, will we be allowed to have notes like we did for the midterm?
Yes.
All right, thank you.
You're welcome. All right, let's do some exercise. The exercise, exactly this. Oh, only this one too is a little bit different. All right, I'll give you a couple minutes to try this. 1 and 2. Yeah, this is lecture 10. try, you know, because there's no right and wrong when we do classwork. Yeah, try to use your own language. Oh, hold on a second. I did not share with you, did I? Try first one first. Try first one. Okay. Great. Moises, good. Right. You show your own understanding of this. That's good. Yeah. Xiaoming, you don't need to write down equal sign before the, because you have inequality, right? You have left hand side, right hand side. You don't need to write the equal sign. Right, so this is a contradiction, but then you have to end up with, so the original assumption must be false, which in turn proves the proposition. You have to write this in English. I'm not understanding your proof. So you're trying to find a counterexample. You're trying to find, okay, suppose there exists x naught, an integer, and x naught is greater than 0. Right, okay, suppose there is a positive, a real number, and x naught divided by, oh, okay, I see. You're negating the second part, which is greater than or equal to this. Then that will derive, okay, you move this one to the other side, minus, okay. Then you have a common denominator. Common denominator gives you x naught times x naught plus 2, right? Minus x naught plus 1 square, which gives you negative 1 over this. Okay, the denominator is positive, but this one is negative. That tells you. Right, okay, that's good. That's good. So, right, original has to be at least 0, but now you have negative 1 divided by a positive number, which cannot be at least 0. Good job, that's good. But you need to write a little bit more. You need to write a little bit more English to explain what you're doing. All right, so basically, right, you're proved by another kind of, you're still proving by contradiction, but you need to write it more to lead your reader to understanding where you are going to and how are you going to prove the original statement is true, All right, let's see, Maya's. Okay, Maya, you have to end with, so the assumption is false, which in turn proves the proposition. Shamisha, you cannot say let. Okay, this is not solving. This is algebra language. Algebra language, we let x be this, let something. No, in proving, in mathematical proofs, we don't let, we assume. Okay, you have to start with assumption. Samuel. Your proof is not proof, okay? Read the lecture notes. Jinqi also, try to form mathematical proofs. I done same thing. Too simple. Look, Moises. I really like Moises. Okay, Maria is okay. No, Michael, you cannot see therefore that does not exist a positive noun. Oh, maybe you could see that, right? Because this gives you a negation 0. You have to end with 0 greater than or equal to 1. Because that's obvious contradiction, right? 0 greater than or equal to 1. You have to see more about your assumption. So which proves which is saying assumption is wrong, which in turn proves our original proposition. Let me copy voices. Oh, okay. Maybe I already did. Okay, let's see. Ajaya, I didn't see you writing anything. George and Ishrat, Mai Wu. Anybody has any questions? Patrick? Tomorrow is our last class. Oh, okay. So I'll give you a little more time. So for those of you finished, you can go ahead and do 2. Try 2. Maria says, when it says the original assumption is false, does that mean the problem is wrong or where? No. We want to prove the proposition. But to prove for all positive numbers is very difficult. So what do? We want to prove by contradiction. What's the contradiction? How do we prove by contradiction? We negate the proposition. So we assume the proposition is false. Then we derive a contradiction. Because assumption derives a contradiction, so we go back to say, okay, the assumption must be wrong. Does it make sense?
So it's the assumption that made was wrong?
That's right.
Okay.
You see, in this case, this is saying for every positive real number x something, right? We want to assume this whole statement is wrong. We assume it's false. We say, assume the proposition is false. So basically, we negate everything. Then we go from there. Then we'll arrive at a contradiction. And because we arrived at a contradiction, we go back to say, okay, the assumption must be wrong. In turn, to say the proposition must be true. No, Ishrat, we're not assuming x divided by x plus 1 greater than or equal to x plus 1 divided by x plus 2. We negate the proposition. We assume for the is, we want to negate the preposition. Okay, for those of you finished one, you can go ahead with two. Anyone has any questions? Feel free to ask. Are you guys majored in mathematics and physics or biology maybe? Maria, what's your major? Why you are taking this course?
I want to go into engineering at City College, so I have to take a bunch of math and science.
Oh, I see, I see. I see. I see. Because this seems like, you know, to do mathematical proofs, you know, for if you're not mathematical majored, not theoretical physics majored, sounds like no point to learn this. Computer science major is required to learn this. CSCI major, so computer science. What does CSCI mean? Computer science. What about CI?
I think that's like a shorter version.
What short version for what? Short. CSCI means?
Yeah, computer science.
Oh, the whole thing means computer science. I see, I see. My first master's degree was computer science, but then we just use CS. So I guess different schools.
Yeah, notice that at Hunter it's spelled this way.
I see, I see. Jin Chi said you need 1 credit course to graduate. You don't even remember how to do math. Jin Chi, what's your major? Biology, I see.
Yeah, I needed to do this one.
I'm sorry?
No, I needed this 1 credit because I didn't want to do 6 classes next semester.
I see, I see.
Yeah, because I graduate after next semester.
I see. Because my PhD is on abstract mathematics. It's pure mathematics. You know, for students who want to go with a PhD or pure mathematics, you need to know this stuff very solid. Otherwise, I don't really see a good point of it. But anyway, let's try to learn this anyway. Because you know what's good about abstract stuff? It helps you to be really logic. Help you to think very logically. That's one good thing about it. All right. Anybody has any questions so far? So make sure you read the lecture notes to know the proofs, because it's kind of tricky. All right. It's a form language. So mathematical proofs is a form of language people communicate with each other. You have to be able to write this way so other people, you know, understand it, or other people accept it as a proof. Anybody here is mathematical majored? Oh, Patrick. Okay, so you need to be solid on this. Okay, anybody tried to? If you haven't finished one, keep trying one. If you finish one, try two. Yeah, Nino likes to write a short version of proof. That's good. But when you, so next Monday in the exam, try to write more. All right, okay? Try to follow the notes in the lecture notes. Try to follow that steps. You know, it seems like if you're not abstract, I mean, if you're not math major, it seems it doesn't make sense, right? To repeat something, you know, it's obvious. But for mathematical proofs, we need this. We need to repeat certain things or certain statements. Okay, Xiaomin looks good, but then right, like Lino and Xiaomin, you have to go back to finish that to say, okay, the assumption must be wrong, so the proposition is true. I don't see. Oh, I don't need to take calculus 150 next semester. Really? I thought this course required 150 is a prerequisite for this course. No? Or I don't computing accounting majored. Oh, okay. I see. Mm-hmm. Oh, Patrick, you don't understand the calculus example. We don't have a calculus example. Oh,
Yeah,
okay.
you did like differential, and I don't understand that Cal 1 stuff yet because I haven't taken it yet.
Oh, last class when I talk about the continuity and differentiability, right?
Yeah, this isn't this is either a co or a prerequisite. So I think some of us haven't taken Cal yet.
Right. I didn't take it yet, so you haven't taken yet.
No, that's why I get confused with some of the examples you use.
Oh, you know what? Okay, it's good to know because one thing I thought prerequisite is Math 150. I was told actually.
No,
Do you
this
see
is either
in
a
my
pre or a
slides?
co for Math 150.
I see. Okay, I see. Okay, so that example wasn't a good example then. Forget about that example. I see now. Right, the continuity. Okay, I see the differentiability is from 150. I see. Okay, Samuel also taking calculus in spring. I see. Okay. All right.
I recommend a lot of tutor for that one. Yeah, they do help.
Okay. That's great. And this is a winter course. It's hard because every day is something new. So you probably have to put in 7 hours study into this.
Yeah, this is
Patrick,
my third winter class.
oh, this is the winter class? Wow.
Yeah, I wanted to graduate on time. That's why.
Oh, you're not even graduate on time. You're graduate early. Where do I see your problem too? Let me see. Let me go back. I see Shamisha, Jinchis, Samuels, Myers. I don't see your two. Oh, here. Assume. Okay. So P and not Q is true. Okay, this you see in your head, but you have to, in the final exam, you have to tell me what is P, what is Q, all right? So a squared is even and a, so assume basically a squared is even and a is not even. So that's why, that's to say a is odd. If a is odd, a equals 2c plus 1. Then a squared is 2c plus 1 squared. Then simplify to be this. Then a squared is 2. You cannot, a squared equals to, then you see you cannot use c anymore because you use c already. So here, number 4, step 4. Step 4, you write a squared equals 2d plus 1, where d equals to 2c squared plus 2c. All right? Then you go back, see that to say a squared is odd, which contradicts to the assumption a squared is even. So this proves the assumption must be true. The assumption must be false. Because if assumption is false, the original statement must be true. Okay. Other than that, pretty good. Yeah, Maria's looks good. Right, so the assumption is false, which proves the proposition is true. Okay, Michael, okay, I think you guys get the gist of it. Just to make sure you see more about it, okay, in your homework and especially on the final exam. Okay, now let's try 3. Let's try, if you haven't finished 2, keep trying 2. If you finish 2, let's try 3. Okay. You should make sure you use the same lowercase a, all right? In this course, the capital letter A represents a set. George, you cannot say suppose A is odd. You're assuming the negation, right? You suppose A squared is even and A is not even, or A is odd. You have to suppose both. Same thing for Ajaya. You have to assume A squared is even and A is odd. Remember, P and not Q. P and not Q. Jaya, okay. You see, the question is, suppose a is an integer a square. If a square is even, so a square is even is p. Then a is even. So p implies. Let me write it in the chat. So this is p implies q form, right? We want to prove by contradiction. So proof by contradiction is not. We suppose not p implies q. And we see that that's equivalent to, so it's equivalent, this not of this is equivalent to, we want to prove, we want to assume not, then to say not, how do I say that? Not of not. So basically it's not, no, it's p, so we want to show, basically we assume p and not q. So in this case, we assume a square is even and a is not even, or a is odd. Does that make sense? No, no. Okay, Patrick, same thing. You see the statement is if a square is even, then a is even. Let me write here. So P is the statement a square is even. And the Q is the statement a is even. We want to follow P and not Q. So this is our assumption. We assume P and not Q. So what does it mean? We assume a square is even and a is not even. Okay?
Yeah, so
Then,
I thought it
yeah.
starts out with suppose A is not even. And
Oh, no. No, suppose P and not Q. Suppose P not Q. This is, okay, prove contradiction, use contradiction to prove, okay, this is use contradiction to prove P implies Q statement.
assume A
So
squared.
this is just one way to prove, to use contradiction to prove the conditional statement. So we assume P and not Q.
Oh, okay.
Assume P and not Q.
So we're assuming Q is the opposite to prove P is even. Wait.
No, we use this. So we assume something, right? We assume something, then we derive a contradiction. Because
Yeah.
we assume A is even, A squared is even, A is not even.
Wait, but if we're assuming P and not Q, aren't we assuming that A is not even?
No, P is A squared is even. Oh, you mean Q?
Yeah, so A is even, so we're assuming that A is not even.
That's true. That's true. Not Q means A is not even. You're right.
So, okay. But then it's like, so we're assuming A is odd to prove that A squared is even.
Right. We want to do that, but we won't be able to. Right? Because if A is even, A is even, it can be written as 2B plus 1. Then we substitute into A square, we calculate A square, we prove if A is not even, then A square is even. However, we assumed A square is even. We assume P. So that's a contradiction.
Yeah, so when I do the, the math and I get the 2b plus 1, it's wrong to then conclude with therefore a squared is odd?
You're right. Therefore, because a is odd, when you calculate a square, it's in an odd form. But that's a contradiction to our assumption. Remember, we assume a square is even. That's exactly the contradiction.
Oh, right. Right, I get it.
Okay. Okay, Maria, assume A is greater than 2, A divides B, and A divides B plus 1. Da, 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 da. Looks good. Ha! Maria, did you just copy and paste? Even the mistake. You even copied the mistake. I see. Learn from your notes, okay? Learn from your notes, because I know you copied from it because I see the mistake. You even copied the mistake. D minus C is a positive number. Okay, make sure we understand the notes. Now I know your background. I think this is quite difficult for you. Okay, Samuel has problem to understand this question. You mean 3, right? Dan is asking, what is the mistake? Maria, where is the mistake? Oh, okay, the mistake, let me show you. It's, okay, here, can you see my highlight? Then maybe I just copy and paste. Just this one. This one, this is supposed to be both A and 1 are positive. D minus A is positive. There's no A in it. This A is not supposed to be there. Just D minus C. D minus C is positive. It's not D minus CA. So that's a typo in the lecture notes. Okay, Samuel has a question with 3. 3, we want to prove this proposition, right, by using contradiction method. So what do? We want to assume the proposition is false. Yeah, I cannot change the lecture notes because the lecture notes was sent to me by what do you call it? PhD file. So PhD, you know, it's the file in file. It's done by the coordinator. So like just for you to know, it's just D minus C, all right? It's D only 1 over D minus C in the left hand side. Okay, so now Aidan, what do you want me to write it out? You mean this sentence? Just this A not supposed to be there. Oh, how to do the problem? Okay, let me write out the steps. So let's talk about 3, right? Let's talk about, oh, you know what? So, okay, what do you, so you want me to write it out for which one? For 2, for 3? or in general? For 3, okay, let's talk about 3. So 3, let's go to the blackboard, the whiteboard. So the proposition is this. A is an integer. A is a greater than or equal to 2. Then, oh no, hold on a second. What is it? Oh, it is A greater than or equal to B. Oops, let me start again. So proposition, an integer A, B, A greater than or equal to 2, and B, then A does not divide, A doesn't divide B, or A doesn't divide B plus 1. Okay, so this is a proposition. Doesn't divide means it's not a factor of it. So A is not a factor of B, which means B cannot be written as A multiplied by an integer. So we want to prove by contradiction. Prove by contradiction. Let's see, how do we do it? First step. We want to negate this proposition, which means we assume, because it's difficult to prove. It's difficult to prove in by direct proof, right? Because there are infinite many integers. So B, there are infinite many B's, there are infinite many A's. So we want to prove by contradiction. How do we do it? We assume the proposition is false. So we assume the proposition is false. Which means, what does this mean? So we assume the proposition is false. What does it mean? How do we assume the proposition is false? So basically we negate, right? So we assume we assume an integer A greater than or equal to 2, B, A divides B, A divides B, because before was or, now the negation becomes and A divides B plus 1. Let me put parentheses for this. We assume there is we assume there are integer. I shouldn't use a. Right, okay, in the preposition, I shouldn't use a non-integer because both A and B are integers. So basically, A and B are integers with the extra condition A is greater than or equal to 2, so which means A is at least 2. So we assume the proposition is false. So basically, we negate the proposition. How do we negate? The negation becomes, we assume they are, okay, I'm missing they. We assume there are integers of A and B with A greater than or equal to 2, such that A divides B and A divides B plus 1. All right, so we negate the whole statements. So then our goal is to arrive. So the goal, our goal, let me read more. So we want to arrive at a contradiction to show this assumption is false. Right? So we want to use this assumption to derive a contradiction. And because there's a contradiction, so that goes back to see the assumption must be false. And our assumption is false, which in turn to see the proposition is true. Because our assumption says the proposition is false. Does this make sense? Anybody has any questions so far? Okay. So now, so what we want is to arrive at a contradiction. So how do we form a contradiction? So step two, A divides B, right? A divides B give us this. A divides B give us B, so equals to some A times C for some integer C. And the same thing, hold on one second. A divides B plus 1, right? So A divides B is to say B equals to AC for some integer C. Similarly, A divides B plus 1 gives a B plus 1 equals to A times D. Let's use another letter for some integer D. So A divides B plus 1 is to say B plus 1 equals to AD, right? A is a factor of B plus 1 for some integer D. Make sense? Anyone has any questions? Now let's do some calculation, right? Let's do, so B equals to AC, B plus 1 equals to AD. Let's do B plus 1 minus B. Right? B plus 1 is AD. B is AC. Right? So B plus 1 minus B equals to AD minus AC. Well, let's simplify this. B plus 1 minus B, that's 1. So 1 equals to AD minus AC. Well, now let's factor out A, because A is a common factor, right, on the right-hand side. The D minus C. Right? So step 4, 1 is positive, and A is positive. Remember we said A has to be at least 2. 1 is positive and A is positive, so D minus C has to be positive. And a positive integer, right? So 5. So now let's divide D minus C on both sides. So we get A equals to 1 divided by B minus C. Think about positive integers. Right? Here you don't have to write it, but think in your head. Thinking positive integers. Right? The smallest one is 1, 2, 3, so on and so forth. Did I write D minus C? 8. Oh, B, I'm sorry. Oh, hold on a second. D minus C. Right, I wrote wrong on the on one of the. Let me use this. Yeah, sorry. Oh, sure. Can I recover this? Oh, I cannot recover it. At the wrong button. Okay, no, don't worry, don't worry. So proposition for integers a greater than equal to 2, b, then a divides b, or a, no, a does not. A does, then divide b, or a doesn't divide b plus 1. Okay, so that's our proposition, and we want to prove it by contradiction. How do we do that? We assume the proposition is false. How do we assume the proposition is false? We assume for integers a greater than or equal to 2, b, a divides b, and a divides b plus 1. All right? We assume this. Let me write it in red color. We assume this in the hope to derive a contradiction. Okay, so that's why we do this, in the hope to derive a contradiction. So step 1, let me write it in blue color. Step 1, we assume that for integer, oh, I already did that. We assume for integer a greater than or equal to 2, b, a divides b, and a divides b plus 1. So a divides b means b equals to some ac for some integer c. Okay, then a divides b plus 1 means that b plus 1 equals to ab for some integer d. Okay, so you see we read b as equals to ac, b plus 1 equals to ad. Right, now so let's do some calculation. So let's do b plus 1 minus b. b plus 1 minus b, that equals to ad minus ac. Right? We simplify. b plus 1 minus b, that's 1 equals to ad minus ac. Let's factor out a. So we get 1 equals to a times bc. Well, 1 is positive and a is positive. So b minus c has to be positive. Right? You can think some positive integers. So which means the red color means you think in your head. Means D minus C can be 1, 2, 3, so on and so forth. So 5. So let's rewrite A. So let's divide D minus C on both sides. So we write A equals to 1 divided by D minus C. Right? So think about this. So now let me write it in red color. So this means 1 divided by D minus C can be 1 over 1, which is 1, 1 over 2, 1 over 3, so on and so forth. 5, 6, right? So see that? Which means, so A can be A, well, let's do this. A less than 2, right? You see 1 over D minus C can be 1 over 1, which is 1, 1 over 2, 1 over 3. So at the most 1, at the most 1. So A equals to 1 over D minus C. That means A less than 2, right? But we assumed A is greater than or equal to 2. So this is a contradiction. So A, this means our assumption must be wrong, must be false. Then 9 in turn, because our assumption negates the proposition, right? Our assumption says that the proposition is wrong. So now it's wrong, wrong. So this is saying the proposition is true. So this proves the proposition is true. Okay, done. That's it. Oops, what's going on? Why it shifted? Oh, okay. In step 3, how do you know that A is positive? We assume A is positive. You see, A is greater than or equal to 2. You see in the first line, A is at least 2. Okay. Oh, you're welcome. Okay, any questions? So this is approved by contradiction. Assume something, arrive at contradiction, then the contradiction is saying the assumption must be wrong. Okay, anybody else has any questions?
Yeah, I got a question about the final.
Oh, the final, right.
Based on your, memory, the final is going to be everything we had on the midterm plus the 3 types of proofs we've learned and counting lists.
Suppose so. Let me check. Yeah, lists,
And the 3 types of
combination,
proofs.
permutation. direct proof,
contrapositive
positive
proof,
proof, right?
and contradiction.
Contradiction.
And I'm sorry, what was commutation?
Permutation, remember, out of 5 people, choose 3 to go on a swimming team.
Oh,
Like
yeah. Okay.
Right, then induction. Oh, you know what? It's not commutative. It only starts with lists.
Yeah, isn't commutative
Yes,
part of
I
list?
lied to you, right? I lied to you. Usually my final is commutative, cumulative. But she designed to be separate.
Oh,
So
cumulative. I thought you said commutative.
yeah, I'm sorry, but I used the wrong words. You know,
The
I'm
only-
Chinese.
The only thing I remember after midterm really is we did lists and we just did 3
You're right.
proof.
You're right. So everybody pay attention. It's not cumulative. The final is just the last half.
Oh, it's not cumulative.
It's not cumulative.
Oh, before you said it was.
Before I said was, right? That's why I said I lied to you.
Oh,
But
okay.
usually from my personal, if I design the course myself, my final, is always cumulative.
Right.
But this coordinator, she designed not so.
Oh.
So the midterm, the material on the midterm is not on the final. It's not on the
material
final.
The final is not is. Oh, wait. Oh, okay, I get it.
Yeah, you're right. 10 questions like midterm.
Okay, thank you.
From the lecture of lists, from lecture 7, right? Lecture 7, yes. So 5 lectures.
Okay, thank you.
You're welcome. So less to study. Okay, good questions.
Do we still have the same time?
Oh, same time, right? Six. Not even 10 questions. But she has a different part. She has like A, B, C, D part. The total six big questions, but under some questions there are the different parts. Okay, so tomorrow is our last lecture. We're going to talk about induction. And so today, study for contradiction, direct proof, contradiction, direct proof, contrapositive, contradiction. So tomorrow we're going to talk about induction proofs. All right. Any other questions? I guess everybody submit your homework, right? So after the class, I'm going to post solutions for your homework. Right, you could think there are 4 kinds of proofs, but remember the contrapositive. Contrapositive is equivalent to direct proof. Remember, if P, then Q is equivalent to if not Q, then not P. All right, so if you think this way, there are only 3 kinds of proofs. Okay, any other questions?
I have a question.
Yeah.
When do we use permutation, the formula for permutation?
Formulas for permutation, let's say this way, right? Let's say I give you 4 letters. You have 4 letters to use. I'm asking how many ways you can choose, you can make a 2-letter words out of these 4 letters. Let's say I give you A, B, C, D, right?
Yeah.
I'm asking how many words, how many two-letter words you can make out of these four? Out of this A, B, C, D. You can make a AB, AC, AD. You can make a BC, BD. You can make a CD. And then the other way around, right? CD and DC are two different words. I mean, it's not words, right? You understand what I mean? I'm just making examples here. That would be permutation. Permutation means the order matters.
Okay. So the number will be larger compared to combination, right?
Exactly. Combination is like, how many, so out of these four letters, I'm asking you to choose two letters. So how many ways to choose two letters? I don't even talk about words. As long as you choose two letters, those two letters are equally weighted. So that would be combination, which means the order does not matter.
Okay.
Yeah. Okay, so tomorrow will be our last lecture, and we're talking about induction proofs. Hopefully you have a time to do your homework and plus read ahead of the induction proofs. And also at the same time, try to study. If you have any questions, we can talk about tomorrow also. All right, I guess I'll see you tomorrow.